Welcome to the Explainer. Today we're going to take something that, well, it often just looks like completely abstract, boring algebra on a chalkboard, right? And we're going to transform it into this brilliant cinematic toolkit to decode the physical world around us. We are absolutely mastering the three equations of motion today.
Okay, let's dive right into our roadmap for this explainer so we don't get lost in the jargon. We'll start with the language of motion, move to the time equations, unlock the timeless equation, bring it all together in a unified physical story, and finish up with the golden rules.
All right, Section 1, the language of motion, setting the stage. Before we look at the actual equations, we really need to understand the rules of the world they live in.
So these equations belong to a field called kinematics. It's basically the study of motion where we completely ignore what is causing the movement. No pushes, no pulls, we're just looking at the movement itself. But listen, here is the absolute most critical part. These equations only work under the strict, totally non-negotiable condition of uniform acceleration. The acceleration literally has to remain constant, and the object must move in a straight line. That is the foundational backbone of everything we're about to cover today.
Before we start combining them, let's meet our cast of characters. We've got 5 variables to play with here. U is our initial velocity, so right at the start when the clock is at 0. V is our final velocity, at whatever later time we're looking at. A is our constant acceleration. T is the time elapsed. And finally, S. Now pay super close attention to this one. S is displacement. It's not just the total wandering distance traveled, it is the exact straight-line shift from the starting position to the ending position.
Moving on to Section 2, the time equations, tracking the action. Both of these are going to rely heavily on the clock.
Meet Equation 1. V equals U plus AT. I like to call this one our time tracker. It's actually just a super simple rearrangement of the basic definition of acceleration. Since acceleration is just the rate of change of velocity, meaning A equals V minus U divided by T, we literally just multiply both sides by T, move the U over, and bam! Simple, right?
Now, what's really interesting about this is what gets left out. This equation perfectly connects velocity and time, but the missing variable? Displacement. It's S. It completely ignores where the object actually is. Physically, it's just telling us that every single second, the velocity changes by an amount equal to A. So let's say you start from rest, 0 velocity, and you accelerate at 2 meters per second squared. After 5 seconds, you just do 2 times 5. You're going 10 meters per second. It tells us exactly how fast something is moving at any given tick of the clock. But what if we do care where the object is? Well, enter equation 2. S equals UT plus 1/2 AT squared. Think of this equation as the map. It tells you exactly where an object is located at any specific point in time.
And this brilliantly illustrates exactly where that map comes from. If you picture a velocity time graph in your head, the displacement is just the area underneath the line. Equation 2 literally just splits that area into 2 basic shapes. The first term, UT, is a rectangle. That's the displacement you would get from your starting speed alone, as if you never accelerated at all. And then that second term, 1/2 AT squared, that's a triangle. It represents the bonus distance you gained or lost purely because you were speeding up or slowing down. All right, Section 3, the timeless equation, the magic trick. This is an incredibly powerful tool for a very specific kind of problem. So here's a scenario for you. What if you just don't have a stopwatch? Think about a real-world example here. A car is cruising at 20 meters per second and suddenly slams on the brakes to come to a dead stop. You need to find the braking distance, the displacement, but you have absolutely no idea how long the whole process took. Equations 1 and 2 are suddenly completely useless to us because they both desperately need time. Let's move to and see how this builds our third final equation. We take the time variable t from equation 1, which, if you rearrange it, equals v minus u over a. Then, we substitute that somewhat messy fraction right into equation 2 wherever we see a t. Now, I'll spare you the painful algebra, but after expanding the brackets and multiplying everything by 2a to clear out the denominators, it brilliantly simplifies into this clean, timeless formula, v squared equals u squared plus 2as. Look at that! We've completely eliminated time. This is the magic trick linking speed directly to distance.
Think of this matrix as your absolute ultimate cheat sheet. It shows us that identifying the missing variable makes choosing the rate equation just a simple logical deduction. It's not a memorization chore at all. If you don't care about distance, you use equation 1. Don't care about final velocity? Equation 2 is your best friend. And if you don't know the time, boom, equation 3.
Section 4 now, a unified physical story, bringing it together. We're going to look at one continuous event using all three of these lenses.
Picture a ball rolling down a ramp from a standstill. At the very beginning, time is 0, and that initial velocity u is 0. It hasn't even moved yet. As it starts rolling, time passes. Equation 1 is essentially acting as a speedometer, tracking its growing velocity second by second. At the exact same time, equation 2 is acting like a literal tape measure, tracking exactly how far down the ramp it has traveled at each moment. But what if we just want to skip right to the end of the movie? When it hits the bottom of the ramp, equation 3 tells us its exact final speed based purely on the physical length of the ramp itself, without us ever needing to bust out a stopwatch. All three equations describe the exact same physical reality. They're just giving us completely different perspectives.
Finally, Section 5, the golden rules, sign conventions, and limits. Consider this a bit of a warning, because these powerful equations can break easily if we aren't careful.
We really have to follow the rules of the road here. Remember what we established right at the beginning? Uniform acceleration is absolutely non-negotiable. If a car is braking, but the driver is pumping the brakes, so the deceleration is fluctuating, these equations fail. If the motion curves away from a straight line even a little bit, they fall apart. And crucially, all of your variables have to refer to the exact same directional axis. Now, in the real world, the most common application of these equations is gravity. A fantastic, everyday approximation of uniform, constant acceleration is an object in free fall near the Earth's surface. Assuming we ignore air resistance, our acceleration a becomes negative 9.8 meters per second squared.
So the crucial point is how we actually handle those positive and negative signs. You absolutely must define your positive direction first. Usually we just say upward is positive. That means if an object is thrown straight up into the air, its velocity is positive, but gravity is pulling it down, so a is negative g. If it's falling down, well, then both its velocity and its acceleration are negative. Applying this sign convention consistently from the very first second to the last is the single biggest secret to avoiding those common, incredibly frustrating mistakes on complex physics problems.
I'm going to leave you with this final thought. These three equations, they are an absolute masterpiece for uniform acceleration. But what happens to our math when an object's acceleration changes dynamically at every single millisecond? Well, solving that exact, wildly complex problem is exactly why Isaac Newton had to sit down and invent calculus. And honestly, that sounds like a perfect topic for a future explainer. Keep learning, and I'll catch you next time.